Liquid, solid, and gas, states of matter. We are going to look at just the properties of the different phases and what makes them different today. And then we'll look at changes of state tomorrow. Maybe. There we go. So the kinetic molecular theory, what does kinetic mean? If we look at kinetic energy, what does that mean? Moving. So something's moving. So all these molecules are always moving. We're looking at the molecules moving, and that's called the kinetic molecular theory. So a particle of matter is always in motion. An ideal gas will fit all assumptions. So when we talk about the properties of gases, we're talking about ideal gases. Real gases actually exert some forces on each other and do have some attraction and repulsion with each other. But we're going to look at ideal gases that they'll follow. Noble gases will behave like ideal gases. So there's 5 assumptions. And these are assumptions of gases. And they consist of a large number of tiny particles far apart relative to their size. So these particles are really tiny, and if they're really tiny, they're really far apart. So even if they're a little bit larger molecule, they'd be even a little bit farther apart. So they're just really far apart. The collisions between particles and with the container are elastic, meaning there's no loss of kinetic energy, so their energy before the collision is the same as after the collision. There's no transfer of energy. And gas particles are in constant, rapid, random motion, which is why if I were to open a bottle of vinegar in the back of the room, would you end up being able to smell it? You wouldn't smell it right away, though, would you? Take a little bit. But that's because they're in constant, rapid, random motion, so those molecules will eventually diffuse up to our part of the room, and it would smell really bad. Okay, and then there's the 4th assumption is there's no forces of attraction or repulsion between the molecules. Gas particles are in constant, rapid, random motion. That's what that last one was. Constant, rapid, random motion. Okay, so there's no forces of attraction or repulsion. You're not trying to, the molecules aren't polar, because polar molecules are able to attract other polar molecules, so there's no forces of attraction or repulsion. And then the average kinetic energy will depend on temperature. Since kinetic energy is, the equation for that is 1/2 mv squared, the speed, the kinetic energy is also dependent on the speed, and the speed of the molecules is dependent on temperature, so that's how they're all interconnected. The faster the speed, the faster the kinetic energy, the higher the temperature. Slower the speed, lower the kinetic energy, and lower temperature. So they're all directly related. Can I change it? So some properties of gases. Gases are able to expand. They don't have a definite shape. You can put it into any size or shape of container, and it's always going to fill that container, right? Fluidity, the particles will glide past each other, so you're able to pour gases. If you think about the liquid nitrogen that we had last week, when the liquid nitrogen is gone and we were pouring out the smoke or the vapors, you could see the molecules moving. You could see the molecules moving past each other. Okay, they have low density. In most cases, the density is close to 1/1000th the liquid form, which is why when you have a gas in a liquid, it would rise to the top. Gases would always be lighter than the liquid, or less dense. And then compressibility, the volume can be compressed 100 times the volume. So since the molecules are so far apart, you're able to kind of squeeze them so that they get closer together, get rid of some of the extra space, and compress them. They're able to diffuse and effuse. Probably really familiar with diffusion, which is like with that vinegar example where the gases will just move and diffuse across the room. Spontaneous mixing from random motion. Effusion, you're probably not as familiar with the terminology, but you know what it is when particles under pressure pass through a tiny opening. So gas particles under pressure that would pass through tiny openings. Can you think of an example of that? Can you think of an example of effusion? Where the gas particles pass through tiny openings. Balloon filled with air. Eventually, what happens to that balloon?
It goes flat.
Why?
Because air flies through the balloon.
Yep, there's little tiny openings in the balloon that eventually all those gas particles can escape through. That'd be effusion. If you have a nail in your tire, eventually it'll go flat. You might have a really slow leak. That would be effusion. Now, if you take the nail out, it's not going to be a slow leak anymore. It's a big hole. The rate of effusion and diffusion will depend on the speed of the molecule. So the faster it's going to diffuse or effuse. The diameter, a larger diameter molecule is usually a little heavier, so it's going to move slower. So it's going to diffuse or effuse slower. And if there's any attractive forces between the gas molecules, they'll diffuse or effuse slower also. Okay, real gases. So we've been talking about ideal gases. And just briefly, real gases, they will occupy space and exert some attractive forces on each other. So they might not follow all these assumptions exactly, but pretty close. Noble gases are the gases that will behave ideally just because they are all nonpolar. They have their molecules with them. I mean, they're not attached to any other or bonded to any other molecule or atom to make a molecule. So they're by themselves. And then if you have a more polar compound or molecule, you'll have more attractive forces between them. So they'll behave less ideally. Okay, liquids. Liquids is a form of matter that has a definite volume and takes the shape of the container. If you put liquid into a container, it's going to fit the shape of the container, right? So it has an indefinite shape, but will it completely fill the container if you only fill it half full? No, it doesn't expand to fill the whole container. So it has a definite volume, but it has an indefinite shape. Liquids are the least common state of matter in the universe actually. Okay. And Earth is 70% covered in water, so liquids outside of Earth are very, very rare. They have a lot more attractive forces between the gases, and those are called intermolecular forces. Intermolecular, if we think of, what's the difference between intramural sports and intramural sports? If you go to college, are you gonna play and you're not on the college basketball team or football team? And you want to play inter or intramural sports? It's intramural. What's the difference between the intramural and if the college-sponsored sport would be intramural? What's the difference? Right, intramural, you play other colleges or other schools. So you're going outside of the school to play other schools. Intramural, people within the school. So intermolecular are forces that are outside with other molecules, one molecule attracting another, where intramolecular forces would be the bonds between atoms within a molecule. Okay. There's more attractive forces which hold those molecules a lot closer together, which is why they've condensed down into a liquid form. Compared to gases, they have a lot higher density, 1,000 times denser than gases. They're relatively incompressible. Once you have a specific volume, you can't really compress the liquid even farther to make it a smaller volume. The molecules are already close together, so they can't really compress down any farther. And then they are able to diffuse. If you have a cup of water and you put a drop of food coloring in, what eventually will happen? The whole cup will be a different color, right? And they're two liquids, so the liquids are able to diffuse through the whole system. Can I switch it? Not quite. Okay, the process is a lot slower in liquids just because they're moving slower. Gases, they're moving a lot faster, so it's able to diffuse faster. It is able to diffuse. Can I switch it now? Okay, there's surface tension. Surface tension is a force that pulls adjacent parts of a liquid surface together, decreasing the surface area. This is why water droplets, if you had a water droplet on your desk, it would look kind of bubbled up, right? You'd have a bubble. Or did you guys do in elementary? We did this in elementary. Figure out how many drops of water could fit on a penny before it spills over. Okay, and it bubbled up, kind of. That was surface tension. So all the forces are pulling to the inside of the water droplet, and you'd have some surface tension on the top, making it not fall over until you reach too much. It's also why water bugs, when they are able to kind of stand on the surface of the water because of the surface tension of the water, or rain droplets stay in a little drop because of surface tension. Capillary action is the attraction of a surface of a liquid to a surface of a solid. So, were any of you guys able to give blood at the blood drive? Did they have to take a little, and did they use a little tiny tube that they put up next to the drop of blood, and then the blood got sucked up, right? They didn't suck it up, did they? It just, all by itself, it went up? That's because of capillary action. Your blood is attracted to the glass of the capillary tube and gets drawn up. Yep. That's also why when you measure out water in a graduated cylinder, what does it look like? Doesn't it have a meniscus like this on the top? Because the water is attracted to the glass, so it goes up the glass a little bit because of the capillary action. Now, if you were to look at mercury, if you put mercury, you can't do this obviously, but if you put it in a graduated cylinder, it's not attracted, it's actually repulsed by the glass, so it looks like this when it's in there. Whoops. Yeah, you can get in big trouble letting you guys play with mercury. Yeah, I gotta go back. It's poisonous.
It's not like anybody's gonna eat it.
Okay, liquids are able to evaporate and boil. Those are both forms of vaporization. So vaporization is the general term, and then there's two forms of vaporization, evaporation and boiling. Evaporation takes place at the surface of the water or liquid. So all the water molecules the liquid molecules are turning into gas molecules. That's vaporization. When it occurs at the surface of the water, that's evaporation. If it occurs at the bottom, that's boiling. So when you boil a pot of water, the bubbles form at the bottom, right? So the bottom liquid is turning from a liquid to a gas, and since gas are less dense, then it bubbles up to the top. So evaporation happens at the surface, boiling happens at lower, whether it's the bottom or in the middle, that'd be boiling. And then formation of solids, so when liquids turn to a solid, that's called freezing. And so the energy, when you decrease the temperature, the speed and energy of the molecules slow down. Since they slow down, the forces between them become stronger, and it holds them together into a solid. Okay. So properties of solids: very closely packed. The energy and the speed of the molecules have slowed down, so they're really closely packed. There's two different types of solids. There's crystalline solids and amorphous solids. Crystalline solids are when they consist of orderly geometric repeating patterns. So like salt. Salt is a crystalline solid because it always forms a cube. Even when you break it down, it's going to form cubes. Or if you make rock candy, like at the museum, do you ever buy rock candy on the stick? That would be a crystalline solid. Amorphous solids, their particles are arranged randomly. Some examples are glass and plastic. And then that candy we made, the Christmas candy stuff, that was amorphous solid because any sort of hard candy like that would be, like Jolly Ranchers, would be amorphous. Okay. Solids have a definite shape and a definite volume. If you put it in a container, is it going to take the shape of the container? No. It has a definite shape. Also has a definite volume. Very incompressible. You can't compress it by squeezing it together. The volume will slightly change with temperature. Especially, you can see this in older houses, like when you have doors that in the summer they kind of stick, or they won't close completely. Have doors that stick in the summer, or they won't shut completely in the summer, but then in the winter they'll close just fine. It's because of the temperature change and humidity change. It's a solid, but it does expand and contract a little bit. Concrete does that. That's why you get cracks in your concrete. Then definite melting point. I guess the cracks in the concrete come from water getting in and expanding too. But it has a definite melting point. You have to add energy, and then at a certain melting point, you'll overcome those attractive forces and it will turn to a liquid. Crystalline solids have a more definite melting point. Amorphous solids do not. They have a range that they'll melt over, and they're called supercooled liquids. Okay, another example of older houses. Does anyone live in an old house? Yeah. Have you ever looked? Are the windows still old though? Some people replace their windows. Yeah. Have you ever looked through windows and like you move your eyes up and down, or you move your head side to side and it gets wavy? You see that wavy look? Yes, the glass has it's flowed very slowly, and so there's different thicknesses of the glass now. The window panes have different thicknesses, and that changes the way you're looking through it, how the light gets reflected and diffracted. Oh. Go back. Okay, they have very high density. They are the most dense in the solid state, except water. Water is an exception, and we'll talk about that later in the chapter. But if you take like the liquid form and the solid form of the same compound, we're not looking at two different things because two different compounds could have different densities, but it'd be more dense as a solid. And then it will diffuse. So if you have two solids that are sitting next to each other for a really long time, the molecules will diffuse with each other, but it's very, very slow, and it'll take lots and lots of time. You probably won't be able to even determine that. Okay, so some properties of the crystalline solids. Exist as single crystals as groups. They have a lot of different classifications based on its shape, and I think your book goes through that if you want to look at some of the different shapes. We aren't going to go into that much detail with them. So those are called the 7 types of symmetry. That's how they're classified. We aren't going to get into that. The unit cell is the smallest portion of the crystal that shows a 3D pattern. So if you can get down to the very, very smallest part of the crystal, that's called the unit cell. Okay, they can be described by the types of particles and the bonding between them. So we have ionic crystals because they'd have ionic bonds. And so the positive and negative ions are arranged in a regular arrangement. They'd have high melting points and are usually good insulators. Example of that would be salt, sodium and chloride. They would have ionic bonds, and so you'd have an ionic crystal because they do form crystals. Covalent network crystals have covalent bonds. Some examples are diamond and quartz. And they're usually giant molecules, very hard and brittle, have high melting points, and are non-conductors. A lot of ionic crystals are also hard and brittle. Can I switch it? No, not quite. Okay. The diamond and the quartz, they have a lot more complex shape than like sodium chloride. It's not going to be a simple cube or anything. But they would, in your book, they'd have a picture of it. Okay, metallic crystals are from metal atoms. They are surrounded by a sea of valence electrons because metals, if you look at the transition metals, they're in the D block. They have a lot more open orbitals that electrons are able to move back and forth, and that's why they have these certain properties like high electric conductivity because the electrons are able to move around a lot. That's why they have high luster. They just have a lot of unique properties because of that sea of valence electrons. And then covalent molecular crystals are bound by intermolecular forces. If you have nonpolar molecules, they'd be only a London dispersion force is just the name of one of those intermolecular forces. And then if they're polar, the other 2 intermolecular forces are called dipole-dipole forces or hydrogen bonding. But those would be polar intermolecular forces. And they usually have low melting points, are soft, good insulators, and easily vaporize. Can I switch it? And then I think the last part we're going to do today is look at amorphous solids. So if the difference between amorphous and crystalline, amorphous don't have a regular shape. Crystalline would form geometric patterns. They will hold their shape over a long period of time, but they're able to flow very slowly, just like we talked about the glass flowing. And glass and plastic are examples of that. So hopefully, you could, like a lot of this that we've gone through, you probably already knew. Some new stuff, but some of the properties I'm sure you are familiar with. And you can see this chapter is a little shorter than the other chapters, but we'll do a lab or 2 also.